ไม่รู้ Jasper, should I start?
Yes, you can start.
Okay. So hello, welcome back everyone for the fourth day. So today the goal is to, let me just summarize what we've done until now again. We're trying to understand this picture, right, which is the phase diagram of the Spike-Wigner model. And so there are three curves on this picture, which represent the mean square error reconstruction on some estimators as a function of the signal-to-noise ratio. The black one is the minimum mean square error, which has this discontinuity somewhere there that separates the statistically impossible region where it is 1, as bad as it can be, and then it's not 1 anymore, and the transition between the two is the information theoretic threshold. And the goal of today will be to obtain a formula for this curve. So we're going to derive the mutual information of the problem, and then by the IMMSE formula, we'll directly get access to this curve here. Okay. Something we've already done is to study the blue curve, which is the performance of spectral PCA, and to do so, we've used random matrix theory, and in particular the theory of the BBP transition, which is this transition that separates the regime where the spectral estimator corresponding to the eigenvector with largest eigenvalue in the data. This BBP transition separates the region where it's 1 anymore. Okay. And there's a third curve, the AMP curve, which is an efficient Bayesian algorithm, which also has a discontinuous transition like the MMSE, but at a higher signal-to-noise ratio that I called lambda algo, which matches in this specific case the BBP transition. And by case, I mean the specific prior for the signal. So the blue curve is analyzed, and the black curve is what we're going to do, and I will discuss a tiny bit the red curve tomorrow. Okay. All right. So that's the goal of today. But before, so yeah, the goal is of today. Analyze the MMSE for the spiked Wigner model using the replica method. So again, the goal will be to first derive a formula for the asymptotic mutual information between signal and data, and to use the IMMSE formula, which gives us that the limit, so the derivative of the mutual information with respect to d lambda is 1/2 the MMSE of the rank 1 matrix given its noisy observation in the spike model. And will be able to take the limit and show that this is also equal to the limit of the derivative. Sorry, to the derivative of the limit, but this limit is there. And this follows directly by the fact that x star y, if I think of this as a sequence of function indexed by the size, okay, these are limit when n go to infinity. This is a sequence of concave functions. And concave functions, the limit of a concave of a sequence of concave functions is itself a concave function, and so in this case you can exchange limit and derivative. Okay, perfect. So really, all this was discussed already. So really, the goal to obtain the MMSE is to obtain the limiting mutual information. Okay, because so this is the replica formula that I've discussed at the beginning. Because once we have it, we directly have the MMSE. Okay, perfect. So before doing this, let's look at a simpler problem. Where we do not need the replica method. Okay. Just to to see the difference. And this problem is again the ferromagnetic Ising model that we discussed yesterday. So the Hamiltonian of sigma is minus j over n sum I different than j, and I can divide by 2, summing over I less than j or I different than j, and dividing by 2 is the same. Yes, and perfect. And we had also an external magnetic field. Okay. So the Gibbs measure, you remember, or the Gibbs-Boltzmann distribution is P sigma equal exponential minus beta h sigma divided by the normalization. Okay. And the object of interest here would be to compute the free entropy, which is just the log partition function. Let's take beta equal 1 for simplicity. From now on, it's just we drop one symbol. Okay, but you can carry it if you want in the analysis. The free entropy would be 1 over n ln of z, and we want to look at its limit. Okay, so that's the goal. So let me show to you that in this very simple model, and by simple I mean it's one of the simplest statistical mechanics problem, but it's still a complex model, not in the sense of its analysis being complicated, but it's still complex because it's representing large populations of variables interacting in a non-trivial manner through these pairwise interactions. And therefore, there is complexity and there is a phase transition, as we've seen. We have different phases. We have the ferromagnetic and paramagnetic phases, okay? Depending on whether the magnetization, which is the average magnetization, the sum of the spins divided by the number of spins, is zero or non-zero. So it is a complex system with phase transitions, but its analysis remains simple, okay? So I want to show you that in this case, you don't need fancy tools. You can just solve it directly. And we will, in the spike beginner model, in contrast, you cannot do what I'm going to show you. And therefore, you need a smarter method, which is the replica method. Okay, so easy solution. Let's see how it works. Maybe some of you know already this, I don't know. So it's very simple because you see, once you identify, the key point is to identify the order parameter. So by identify the order parameter, it means identify the quantity which is enough to track, to analyze, to keep track of in order to solve the model. And here the model, the Ising model, tells you right away what it is, because you can simplify it very easily if you see it. So let's see. You see that I can rewrite. So the magnetization that I remind you the definition of is the correct order parameter, because you can see it simply from the fact that if you try to simplify the Hamiltonian, you can do so in terms of this order parameter only. What you realize is that the Hamiltonian, the energy function of the problem, which defines the problem, so is just a function of this magnetization, actually. So really, this Hamiltonian is not really a function of the configurations. In this case, it's really a function of the magnetization. Okay, so let's see this, because I can rewrite. So H sigma clearly is minus J. So you see this double sum up to one diagonal term, which I can add and remove, is the square of the sum. So it's the square of the magnetization, right? So this is minus J times N over 2 sum over I of sigma I sum of I of sigma I over N squared. Maybe I can add J over 2N sum of I sigma I squared to compensate for the diagonal term that I counted, but this is just a constant because this is equal to 1. And a shift, like a constant, an additive constant in the energy, does not change the model, right? Because if you add a constant here in the energy function of a system like this, it means you're just shifting the exponent defining the probability distribution, but this constant, meaning it does not depend on sigma, will simplify with the same constant appearing in the diagonal. So constants in energy functions can be forgotten. You don't change anything. Okay? So this constant, of course, can be forgotten. It will be simplified with the normalization. Minus n h sum over sigma I over n. Okay, so this is indeed minus Jn over 2, the magnetization depending on sigma to the square, minus nh, the magnetization. So you see, yeah, the energy is just a function of the order parameter directly. So it means that actually in this model, the probability distribution of drawing a certain configuration, a certain sigma, does not depend on the value of sigma. It really depends on this macroscopic observable, this order parameter. And so you can simplify it, you can solve now the problem directly. How do you do? By Laplace method. Okay, so let's see how do you do. So solving the method, so solving the model. So you want to solve 1 over n, so you want to compute the log partition function. Of exponential, we took beta equal to 1, so exponential minus h, which is Jn over 2 m of sigma squared plus nh m sigma. I can even already factorize the common factor m. Okay, so this is the problem I want to solve. And why can I solve it easily now? Because you see, as I've been able to express the energy in terms of m only, it gives me a natural decomposition of the space of configurations over which I'm summing here in terms of subparts, which are what we called yesterday the macroscopic states, meaning subset of configurations with a given value of an order parameter, in this case the magnetization. So, and then we can exploit this. So let's see. So I can rewrite this as 1 over n log sum over all possible values of the magnetization, okay, which at the moment n is finite, is a discrete set, right? Because the number of spins is finite, so therefore the magnetization can only take a finite number of values, but it's and sum over the associated macro states, meaning subsets of configurations with this given m. So I will write this like this: the set of sigmas such that m of sigma equal m. Okay, and of course, by definition, for each of this sigma, the m sigma is constant. So I can, it means that this exponential inside this sum there is constant. So I can just put this exponential outside there, right? So let me do it. One, right? Perfect. And essentially the problem is solved now. Why? Because this thing you can compute easily. Okay, this is just a problem, a combinatorial problem. You have a sequence of binary variables, plus and minus ones. you're fixing their average, M, and you're counting the number of such configurations with that given average. So it's just an exercise that you solve in the first courses of combinatorics. And of course, so this term in physics is what is called the entropy. Okay, so it's actually the exponential of the entropy. So I can write this as the exponential. Actually, it will be exponential in n as well. So this is exponential n times a certain function that I will call s of m. And if you do the exercise, what you realize is that this s of m is the binary entropy. So it is minus, it is, one second, I don't remember the binary entropy is, yes, is minus 1m over 2 log of 1 plus m over 2 minus 1 minus m over 2 log of 1 minus m. So this is a very simple exercise. If you've never seen this, you should try it, but it's a trivial thing to show. So this term is counting the degeneracy that we call the entropy in physics, the entropy of this value of order parameter. So it's counting, the entropy is basically the exponent that correspond to the number of configurations, sigma, with a given value of the order parameter m. Okay, and of course this number is exponentially large, because given an m, you have exponentially many such choices of sigmas that correspond to this m, and the exponent is called the entropy. Okay. Perfect. The other term now is the energy, and it's already there. Okay, we don't have anything to compute anymore. And the energy here is also expressed as a function of the order parameter. So now we're in a position to solve. So we have obtained 1 over n log sum over m of exponential n times the energy, which we managed to express directly as a function of m. Oops, excuse me. Yes, and I'm sorry. One second. Yes, this is minus the energy. Excuse me. Plus, so I can factorize the n. Plus the Sn. And that's it. Now the problem is solved. Why is the problem solved? Because what I obtain is precisely the type of sums, or this will become an integral when n becomes large, because here it's a sum over all possible discrete values of m that are between 0 and 1. Between minus 1 and 1. Minus 1 corresponds to all the spins down, 1 is all the spins up, and then you have all the possible values of the magnetization in between. And when the number of spins goes to infinity, this becomes a continuum. So in the limit, this will become an integral. So we have the integral, or the sum of an exponential, of exponential terms, which are proportional to n, which is very large. So how do you evaluate this kind of integrals? I've already given the answer, but this is precisely the form where the Laplace integration can be used. So basically, Laplace is just telling you that when you are summing exponentials, which are very large, and you take the order of the exponent going to infinity like this, basically only the term that dominates matter. There is only one term in this sum or this integral that matters because it is exponentially larger than all the other terms. Okay? So if you sum exponentials which are large, and the exponent of these exponentials are large, and you let it grow arbitrarily, basically only one exponential in the sum will matter because it is exponentially larger than the others. Okay? So this, when n becomes very large, is approximately equal, and it's an equality when n goes really to infinity, sum a log of exponential of n, the max with respect to m of this exponent. Okay, so here I'm using Laplace integration. Okay, which is a simple version of saddle point integration in the real plane, in the real for reals saddle point integration. These are, of course, saddle point and Laplace are not exactly the same thing, but they both rely. Saddle point is more general. You can extend, you can integrate in the complex plane, but it's also relying on the fact that you have a large exponentials. Okay, and that's it. So this is equal when n goes to infinity. So this is equal. So the log and the exponential, they simplify, and this n with the 1 over n, they simplify, and so this is max of Sm minus Hn. J over 2n squared. Plus Hn, and the entropy is written there. I will not rewrite it explicitly. It was minus Hn, and that's it. So you have reduced the computation of this high-dimensional sum, or which is the log partition function, into the problem of solving a one-dimensional optimization problem. Okay? And if you do so, if you solve this problem, let's say the solution, let's say that the m, so this gives the free energy, and of course the argmax of this thing is, let me call it m0. It's really, it's what we call the equilibrium value of the magnetization. So it's the magnetization you would observe at a given choice of J and H in the problem. If you were, let's say you simulate this model for large n at a given value of J and H, and you, by Monte Carlo, you sample a configuration of the Gibbs measure, configuration sigma drawn from the Gibbs measure, when n is large, and you compute the empirical magnetization for this sigma, you would realize that this is extremely close to this, to the minimizer of this formula. It's the equilibrium magnetization. Okay? So you see, we could compute in this case easily, we could solve the problem easily, and we have access to everything. Okay? And this m0 as a function of h is what we drew yesterday. So if we fix h, let's even take h equal to 0 as a function of j, we've seen there was the plot we've done was as a function of beta. But okay, in general, this is also a function of beta. If you track beta, and as a function of beta, you remember we had something like this. This would be the M0 as a function of beta at fixed J and H. Okay, so the solution of this simple scalar optimization problem gives you access to this order parameter for this complex system. And really what allowed us to solve the problem directly without using any fancy tool apart from Laplace integration, which is not a fancy tool, is that the original is that the Hamiltonian defining the problem is already written in terms of the magnetization of the order parameter. So of a statistics which is an average over the spins. And so we could solve by Laplace. Okay. But in general, this is not the case. Okay, you cannot identify directly in the Hamiltonian some simple quantity, some simple statistics over which you can integrate like this. This trick only works for a very simple model like this ferromagnetic Ising model. Okay, is it clear what I've done? Okay, so okay.
Any questions from audience?
It seems someone answered that it's clear. I will assume that's the general feeling. Okay, so now let's go back to the spike linear model, which is more complicated and for which you cannot do this. Okay. Perfect. So now the spike Wigner model. Where we will need the replica method. Okay, so let's rewrite the problem. I just want to use the same notation as in the course. Yes. So the posterior distribution in the model, if you remember, is P of X given the data matrix Y is proportional, so up to normalization to the prior, which is factorized over the xi elements by assumption. And then we have product over all pairs, so which are related to our observations. Oops, then there is a bug. Exponential minus 1/2 Yij. And we have our Gaussian likelihood coming from the fact that the noise is Gaussian. Okay, so this is the posterior, which I can simplify a bit. So normalization that will depend on my data that I call Z to use the statistical mechanics notation. And here what I can do, again, like for the Ising model, any term in this exponent which does not depend on x is what I call a constant and can be absorbed can be simplified with the same constant in the normalization. Okay, so I can get rid directly of all terms here that do not depend on x. So if I expand this square, for example, y squared will not depend on x. It will depend on the true x, but the true x is not is a constant. We are talking about the probability of this little x here, while here inside there is the x star, really the value of the ground truth signal, but it doesn't matter in this probability distribution, this term that depends on X star and the noise only, okay? So the y squared term can be simplified with the normalization. Then we have the cross term that depend on X. And then we have the square, which depends on X. So we need to keep only these two last terms. So I can rewrite this as the exponential of minus an Hamiltonian, if you want, that will depend on X and Y. This is my energy function, because now if you want, I'm casting the problem in the statistical mechanics notation in order to use its techniques. And what is the Hamiltonian? It's minus the log likelihood, okay? Minus log likelihood. You get the Hamiltonian. Okay, so that's the definition of the problem, and I can also expand, remembering that this y was equal to square root lambda over n. Of course, in practice, you cannot write down this decomposition because you don't have access to X star and the noise, but here we are doing theory, so we can decompose y like this. It is how it was constructed in our theoretical model, and we are analyzing what is going on. So I can use this decomposition when doing theory. Okay, so in this case, Hamiltonian becomes this. The stars for the ground truth. And the Z is our Wigner matrix corresponding to the noise. So you see again, we have this planted term, the signal component. We call this the planted term or signal term. And this is the noise or disorder term. Okay, in the SK model, this planted term corresponds to just the ferromagnetic bias, and it does not depend on IJ, it's a constant. Instead, here it depends on IJ, and we have this term also in the SK, in the spin glass. Okay, perfect. Like an average or like a magnetization. This is not the case, right? Because even if we have a double sum here, so here we have something that looks like a magnetization, but not here. So let me just emphasize that point. The first term, so let me forget this for a second. Okay, let's put it. We have a term in the Hamiltonian, let's call it T1. We have a term like sum of I less than j that I can write as I different than j of xi star, xj star, xi, xj. And this is indeed, like in the Ising model, something that looks like 1 over n over 2, 1 over n sum of I, xi star, xi to the squared minus a diagonal term, But we have this magnetization that appears. This is like a magnetization. I can call this the M of X, but you see it's a magnetization in the direction now of X star. Okay? But this looks like a meaningful order parameter, and it is one. It is very important to track, because actually the value, this magnetization tells us how much a posterior sample is aligned with the ground truth. So it will be related to the errors that we want to compute. It's an important quantity. But unfortunately, we have also that term, the disorder term. And you see, because this is a full rank matrix, the sum over ij of this term, I cannot decompose this as a square of a single sum. So due to the non-trivial structure of this matrix, this one is rank 1, and because this matrix is rank as rank equal to 1, I can get this decomposition. But this matrix is not rank 1, so I cannot decompose this sum in a simple manner. I have to deal with it. Okay, so that's why you cannot use the Laplace method. Okay, the term 2, the noise term, cannot be written in terms of simple order parameters like M. Like the M of X I just defined here. So I have to find another approach. I cannot do a direct calculation like in the Ising model. Okay, that's why you need the replica method. So somehow we need to get rid of this noise. We need to integrate it out. Okay, this is where the replica method enters. Okay, so let me explain. So goal, get rid. Sorry, other questions? Get rid of the noise, and by get rid I mean integrate it out somehow, and hopefully this should make appear an order parameter. Okay, so let's see if that's the case. So the starting point for this is the replica trick. So let's start now really the replica method. The first step is the replica trick. So I will always tell you what is exact, what is mathematically justifiable and what is not. The replica trick is mathematically correct. Just you can write the replica trick in various ways. Let me write at least 2 ways or 3. I will write 3 ways. Let's say that, so now our goal, again, the ultimate goal really is to compute, like for the Ising model, the free entropy, okay? Because you remember the free entropy in the context of inference, the average of the log partition function, where the partition function is the normalization of the posterior, there, is essentially the Shannon entropy in the problem. And if you have the Shannon entropy, you have the mutual information. So compute the Shannon entropy or equivalently the mutual information. They're all related, or equivalently the so-called free entropy in physics language, which is really an expectation with respect to the law of the data of the log of the normalization of the posterior, which is the evidence, which in this case I called z of y. Okay, and you see that this is up to a minus sign, and maybe so this is essentially minus the entropy of the data, because this is almost up to, this is the p of y. So there are some constants missing. You can look at in the notes. I don't want to go in these details, but up to trivial manipulations, this is an equality. Okay. So the free entropy, so the log partition function from physics, like we computed in the Ising model, really is nothing else than the Shannon entropy of the problem. And if you have the Shannon entropy, you have access to the mutual information and therefore the MMSE. So that's the goal. Okay. So why is this a hard task? Okay. First, because as we've seen, we cannot employ a direct Laplace integration. There is no simple trick here that allows to simplify this term in terms of an order parameter. So we need to deal with this z. And the problem is how to do that. Okay, so you see when I said dealing with this z, we want to integrate it out. And this integration is indeed present in the problem. We do need to integrate it out because it's inside this expectation. This expectation, the expectation over the data, can be written equivalently as an expectation over the ground truth. The data is a function of the ground truth and the noise. So this is the same as an expectation over the ground truth and the noise. And here is this expectation that we need to carry out. Okay. So the replica trick, I will just write it down and stop there before continuing later, is the following exact identity, which is not which is true for any random variable z of y. So the expectation with respect to some random variable, in this case y, but this could be anything. You can completely forget the statistical mechanics problem if you wish. What I'm going to write is true in general. Of the log of a certain function of this random variable, where again this function can be anything, can be written. See, the hard part is that we have to compute the expectation of the log of something. And in general, this is hard because the expectation is a linear operator. The log is not. So you cannot switch them. You cannot push the expectation inside there. Computing expectation of nonlinear functions of random variables is in general complicated. Okay? So you have to find a way out. And the replica trick is just the following identity. Which you can also write equivalently. All these identities can be verified by Taylor expansion in K. Which is also equal. So you choose the form that you prefer. They are all equivalent. Okay, so you see, so first we'll ask you to check this. Check by Taylor. It's just Taylor expansions in K. And you see that the point of all these expressions, they're now computable, or I will show you that they are computable, because now you see what appears is not anymore an expectation of the log on the right hand side. It's always the kth moment of this random variable. We have the expectation of this random function z to the k. So z is a random variable. Instead of computing, if you want, the log moments, this is like a log moment of this random variable z. Now you have the usual moments to compute. Okay, so you have this z to the k here, expectation of z to the k, so it's just the kth moment. Of course, the mathematically difficult part is to make sense of what's the kth moment of a random variable when k tends to 0. Okay, and this is where things become a bit subtle. But think for a moment as k as a finite integer. These are just usual moments of this random variable. Okay, so we kind of got rid of the log in a smart way by introducing this kth moment, but the price we pay is that we'll have to make sense of these moments when k goes to 0. Okay, so this is called the replica trick, and it's the starting point, and we're going now. The goal will therefore be to compute this kth moment and then to make sense of the limit k going to 0. Okay. All right, so that's the idea, and we're going to continue later. So we start again in we start again at 1:30 for you. So in 1 hour.
Yes, sir.
Is it
Yes, sir.
correct?
We can start. Yes, sir. Yes, sir. We can start in 1 hour.
Okay, in 1 hour we meet again.
Okay. Sir, may I request everyone to kindly switch on their camera for a screenshot? Okay. Thank you. We would like to see more faces.
I think most of the others are ghosts. I'm not sure they
Yes.
exist.
Okay, sir. Thank you. Thank you for giving your time, and then we will be back in 1 hour. Huh?
Yes, see you later.
Oh, okay. Thank you. Bye bye.
Should I start or wait a bit more?
Yes, sir. I think we will start so that we finish on time.
Okay. All right. So let's continue. So I've introduced the first steps of the replica method, meaning the replica trick, which is a way to convert the problem of computing the log moment of a random variable into the computations of usual moments, with a catch is that I will need to make sense of these moments when k goes to 0. Okay, so this is something to keep in mind. Okay, so let's then start the computation. So using the replica trick, now the goal is to compute expectation of z to the k. Okay, and so even if later I will need to take k going to 0, I will assume at the moment that k is an integer. Okay, and we are going to obtain a formula for this. So again, I'm sorry, could I ask some of you to show their face? I see always the same person, a very Miss Madame Professor Kagar. Nice to meet you. If some students could show their face, it would be great, please, because it's really difficult to talk in front of a black screen all day. I would like to see that some people participate. Really, this is important. I cannot force you, but I find a bit strange this experience of not being present in any way. Anyway, okay. Let's continue.
Candidates again requested to switch on the cameras. All the candidates are once again requested to kindly switch on the camera and please respond to Professor John Barbier.
Thank you very much. So, yes, it's nice to see that people are actually there. So, we're computing this moment, and the key point is that we're going to assume that it's a standard moment, right? So where k is an integer number, and later on, so we're going to obtain a formula under this assumption, and we're going to then make the assumption that the formula we obtain is still valid, remains valid when we extend it to real values of k, in particular close to 0. So this will be an analytic continuation from the set of integers to reals under the assumption that the resulting formula remains true when extending to real k. Okay? So that's the main idea. So now that we have a integer k, we can write down this expectation of z to the k in a meaningful way. So what is it? It is the expectation of the integral, so the normalization of the posterior distribution, which is dx px of x, and I will use this notation now to mean. Okay. Expectation of some ij of yij square root lambda over n xi xj minus lambda over 2n xi xj squared. Okay? Perfect. And this to the k. So if I take an integral to the k, this is the same, of course, as just introducing k dummy variable, integration variables. Same thing with xa. Okay? So what I've just done is called replicating, and that's why the method is called the replica method, because you see what I have now, this z to the k there is just the partition function associated with k replicas of my original system. Okay? These replicas, they have something in common in the sense that all these systems, so let me write explicitly, otherwise. xia, xja. You see all these replicas, which are indexed by these variables xa's here, I call that a replica. they share this Y. They all have in common the same disorder, the data in this context. Okay. So now the goal is to compute the average over this Y. Okay. And now this is possible. This is possible because I don't have the log anymore, which was stuck there. So now this expectation can be pushed inside the integral there in front of the exponential. And you see that this Y, what is it? It is a Gaussian variable whose mean is related to the hidden signal x star, and the variance is 1. Okay? So I need to compute with respect to a Gaussian distribution the average of an exponential where I have my Gaussian appearing here times a term. So this is computable. This is possible. Okay? So I'm now moving my average over Y here, and I can rewrite this as product over I less than j of expectation of Yij of this exponential. Okay? So remember that Yij, it's a random variable, which is a Gaussian distribution with mean square root lambda over n xi star xj star and variance 1. Okay, so I have something of the form expectation with respect to, yeah, I mean, I don't need to rewrite. I have this term here to compute. This is just a Gaussian integral. Okay, so it's explicit. So you can do this Gaussian integration, and what you obtain with respect to Yij, what you obtain, let me write it. So using, let me write explicitly the formula that I'm going to use, that you should all know, the integral with respect to, let's say, a z, a Gaussian z exponential minus az squared plus bz is square root of pi over a exponential b squared over 4a. So this is the Gaussian integral formula that you need. And if you use this for every ij here, what do you get? You get there remains an expectation with respect to x star that we haven't integrated. Integral of product over a equal to 1, sorry, a equal to 1 to k. A is called the replica index because it's indexing my replicas of my system, just my copies of the system. Dxa, where really xa is a vector, px xa, exponential sum I less than j of lambda over n xia xja xi star xj plus lambda over 2n sum over, I will write the term here. Yes, excuse me, I'm missing. Sum of A equal to 1 up to K. Sum of A different than B from 1 to K of XA, XI, B, XJA, XJB. Okay, so you see this term, so this term was already there. It corresponds to the mean of Yij acting, multiplying this thing. And the integration with respect to the noise, or equivalently if you integrate directly with respect to this, is the same. You obtain this, so you have this interaction between all the replicas and the signal, the ground truth, X star. And now you have this term, which is quadratic. And you see this quadratic term, it's quadratic in this sum. It's essentially a sum to the square, okay? It comes from, you see, the fact that when you do a Gaussian integration like this, the noise, the Zij that was acting on this for every A, here I'm again missing something, I'm sorry. I can rewrite like this. This Gaussian is multiplied by this whole sum. So when you take this sum to the square, this is how you construct this kind of terms, okay? So what do we get? So really here I've done nothing, it's just a Gaussian integral. You can just do the exercise using this formula and using this distribution for y. There is nothing fancy. But we have done something conceptually important. We started from this partition function, which represents, sorry, yes, here. We started from this partition function, which is just z to the k. It represents the partition function of k copies of your system, which conditionally on the data, on the disorder, are independent. So what they have in common is this disorder here, but if you condition on it, you say it is fixed. This just corresponds to k independent system. It's just an integral to the power k. Okay. But now when we integrate out the noise, or equivalently the data, conditional on X star, we couple these systems, these replicas. So what we do is that we start from k independent replicas sharing the same disorder, and by integrating out the disorder, we couple these replicas. But what we gain is that there is no more disorder, there is no more noise. Okay, you see now this system here, this integral here, there is no more presence of the noise matrix Zij, which was the problem in the sense that it prevented us to identify an order parameter like we did for the Ising model and to integrate directly by Laplace. Okay, so there is no more noise, which is a good thing. So now, hopefully, there's a chance to identify order parameters like we did for the Ising model. And indeed, we will be able to do so. Okay, so these are the next steps. Okay, so the first thing I'm going to do is to make this expression a bit simpler by simply denoting X star, which represents the the hidden signal like another replica. It will be x0, okay? And you see that this expectation with respect to x star is of the same form as expectation with respect to the prior of the other replicas, because we are in the Bayesian optimal setting. So the prior used to generate the signal is the same that the statistician is using when writing down the posterior distribution, and so it's the same as what appears here. Okay, so if we simply change notation and call x star x0, it becomes like another replica. It's just another replica playing a symmetric role with the others. So all this integral simply becomes an integration from a equal to 0 now, which includes this expectation, to k of dxa px xa. Okay, and you see that this term is the interaction between x0 and the other x's. So I can absorb this term into this sum. And so this sum now will start from 0 to k instead of 1. Okay, so all this exponential becomes very symmetric, very simple. From a different than b, from 0 to k now, of sum of I different than j of xai, xib, xja, xjb. Okay? Just using this notation. So I've done nothing, I just changed notation. And you see, now I'm finally in a position to use the exact same trick as in the Ising model. Because what I recognize now is something that looks very much like a square of an order parameter. You see, this sum over a different than b is like a square up to a diagonal term a equal b that I can add and remove to complete the square. But it's really like in the Ising model. I have a kind of magnetization that appears again. And this magnetization is actually the overlap that I discussed yesterday. So let's see that. So let's complete the square first. Yes, so you see here I'm putting a 4 instead of a 2 because this sum over I less than j can be written as a sum over I different than j with a 1/2. Okay? Perfect. And this is sum. So first there are two types of squares here that appear, by the way. There is a double sum here over the indices of my vectors, and there is a double sum here over the replicas. So we are going to treat these two squares one after the other. So we're starting to treat the square due to this double sum here. Okay? So let's do it. So first I leave this sum there untouched. And this becomes sum over I from 1 to n of xia, xib to the square. And of course, here there were terms that were not, there are terms that are counted here that are not present here when I equal j. So I need to remove this I equal j term, because they were not present in the original sum. Okay, so again, I've done nothing. I've just recognized a sum to the square, which I wrote explicitly. Okay. Perfect. So what do you recognize here? So first, is there a question, or at the moment the manipulations are clear? I will assume that if you don't stop me, I can continue, but there is really nothing fancy at the moment. These are just basic algebraic manipulations. Okay. So now that I have manipulated this replicated partition function, this z to the k, which I have averaged with respect to the disorder, the noise and the signal, I am recognizing an order parameter. You see here, this quantity looks like it's an angle. It's an overlap. So it's the angle between the replica XA and the replica XB. So it tells you how much these two replicas, which you should think as, so the physical meaning is that replicas are just conditionally independent samples from the posterior distribution, from the same posterior. So they share the same disorder. You remember that we started from z to the k, and this is the law of just k independent this is, sorry, the normalization constant of the posterior distribution of k independent samples from the posterior. So these replicas, really, their meaning is just different samples from the posterior, from the same law. Okay? So this is the angle between two different samples from the posterior distribution. So if this is 0, it means that each time you sample the posterior distribution, you get a new high-dimensional vector that has nothing to do with the others, with the other samples. So it means somehow probably that the posterior distribution does not contain any information about the signal. If you sample each time orthogonal vectors, they have nothing in common. It's probably that you are in a region, there is no enough information in the data to recover the signal. If, however, when you sample twice the posterior distribution, these two vectors that you get look alike, they have an inner product which is non-zero in the large size limit, it means, so they are correlated, it means that probably the posterior distribution does contain information about the signal. And this common direction, so that they're pointing at, is the signal, actually. Okay? So let's introduce this order parameter. Let me give it a name. So I will call QAB, which is a function of XA and XB, simply 1 over n XA transpose XB. Okay, so this is the overlap between replicas A and replica B, which again, replica means in sample from the posterior. So you see, it's like a magnetization, but it's like in the SK model. You are comparing samples from the measure, and you're checking whether they have something in common. Okay. So it's a more subtle order parameter than the magnetization, because in order to compute it, you see, you need to sample twice the distribution. You need to obtain two independent samples. While the magnetization in the Ising model, you just need to get one. You just sample it once, you compute the mean, and this is a magnetization, and it tells you whether you are ferromagnetic, paramagnetic. Here when you have disorder, in spin glasses or in inference problem where you have data which plays the role of disorder, the only way to make appear the order parameter is to replicate And so the order parameter are functions of more than one replica, in this case 2. So it's a more subtle quantity. It only makes sense, the order parameter appears by comparison between samples, okay? Perfect, so using this order parameter, now I recognize that my replicated partition function, the average of my replicated partition function, is equal to integral over all my replicas from 0 to k of dxa pxxa of exponential lambda over 4n sum of a different than b of q ab to the square. Okay. Minus lambda over 4n sum a different than b sum I of xia xib to the square. Now I will make a simplification. I will assume that this term here does not matter, that I can simply remove it. Why is that correct? So again, the replica method is not a mathematically rigorous method. You allow yourself simplification heuristics, then you get the results, and then you can prove a posteriori that is the case. I claim that this simplification is exactly correct in the large n limit. Why? Because you see this term, excuse me, see there is no more n. It's the opposite, the n is there at the numerator. You see, I define the overlap with the 1 over n. Here I have a 1 over n, but here I have a square. So I put a 1 over n there, and therefore I need to remultiply by n. This is the correct term corresponding to that one. And the other term corresponding to that one is here. But I claim this second one can be forgotten, because you see, this term here will scale, will be of order n, because this quantity, this overlap, should be of order 1. It's the inner product between vectors, so it can be 0, but typically, if there is information in the data, this order parameter will be of order 1. So we expect this term to be of order n. Instead, this term is of order 1. You see that you have a sum over n terms here, and there is a 1 over n here. And of course, these variables, they are of order 1. So the prior, let's say they are plus or minus 1. Let's say they are binary variables, like in the SK model. So these are plus or minus 1s. This is of order 1, all this. It's an empirical average of these squares. So this order 1 quantity can be dropped in front of this order n quantity. What dominates this integral is 1. So we are going to simply forget this term. You can show very easily, rigorously, that you can drop it. This is not a problem. Okay? Perfect. So let's continue. So you see now we are in the very same position as like when in the Ising model we had something like we had decomposed what we had recognized that we could write the partition function as a sum over sigma of exponential of a function of the magnetization. And the trick was to say, let me decompose this sum as a sum over the magnetization itself. And then I need to sum over all configurations that have this magnetization. And this was the entropy contribution. Here we need to do the same trick. Now we have recognized for this replicated system, the energy, which is this part here, is a function of a macroscopic quantity, so a kind of summary statistic, which is this order parameter, this overlap. So we need to decompose this integral, which is the sum in the Ising model there, into an integral over the values that the order parameter can take times the degeneracy of these values. So how many microscopic configurations, microstates in the physics language, simply how many configurations of the x's of the replicas are in agreement with a given value of the overlap, like here. How many configurations of the spins are in agreement with a given value of the magnetization. The magnetization is here the overlap. Okay? Perfect. So the way to do that concretely will be simply to introduce a very almost trivial identity. So let's write this entropy. So right, so the entropy was this term in the Ising model. The equivalent here, so let me define exponential of gamma of Q. So where Q is the matrix B's. As an integration over my replicas times delta functions that enforce this constraint. So you see, what is this? It's an integral that is counting the volume. This is the volume of configurations. Okay, this is the integration over my configuration space. And I'm integrating only the configurations such that their overlap between XA and XB is equal to some value that I fix. Okay, so I'm restricting, it's like I'm cutting the space of configurations into subparts that we call the macrostates. And the macrostates are defined by the value of the overlap. Okay, so I'm enforcing the angle between different replicas to be something that I call little QAB. And I look at what's the volume of configurations that verify these constraints. Okay, so this is the entropy. It's the same role as this. Here I was counting the number of configurations with a given magnetization. It's the same thing. Okay, except that now we're working a bit more generically with possibly continuous variables. I'm computing a volume and not just a number. Okay? Perfect. So now I'm going to introduce this entropy in the previous term, in the previous integral that we have here, by using the trivial identity that 1 is equal to the integral with respect to all choices of this matrix Q. So Q really is a matrix of size, so this is a matrix of size k plus 1 times k plus 1, the total number of replicas. Exponential. Okay, and this is indeed 1, because if you integrate with respect to all possible choices of this matrix, this delta function, this gives 1. and then the remaining integral with respect to all the configurations is 1, because this is normalized. These are well normalized probability measures. So the total volume is 1. If you want the total volume of configurations weighted like this is 1. It's normalized. So I can plug this identity just here. I can put a 1 there without changing this integral, right? So I can do that. Integral product over A goes from 0 to K. Exponential lambda n over 4. Sum A different than B and QAB squared. And then I have an integral with respect to this matrices Q of exponential omega Q, which is all this. Sorry, if I integrate this with respect to 1, so I missed that term. This part is what I wrote there already. Product over A different than B of delta QAB minus QAB, where again remember that when I use a capital Q here, this is really a function of XAXB, okay? While this little q is just a number. Okay, I hope you're still following. I've just introduced, I took the previous integral that I multiplied by 1. I multiplied the integrand by 1. But this 1, I wrote it in a smart way. This 1 is the integral over all possible values of my order parameter of the entropy of this order parameter. Okay? I'm summing over all the space of configurations cut into parts, and the total volume is 1 because I'm working with a normalized volume of probability distributions. Okay. Perfect. So now I'm going to use a trick which is probably one of the most important trick in theoretical physics, but not only, it's used absolutely everywhere. Is the fact that these deltas, they are enforcing these constraints that this function of xa and xb should be equal to this number little qab. But this is not very practical to work with. I mean, the only thing I can do if I keep the delta written in this form is to integrate again q and just come back in the computation. I would undo what I've just done. So somehow we need to write this in another form, okay, that become useful. And the trick in physics, and this is at the basic trick in spin glasses, in quantum field theory, in field theory in general, it's used everywhere, is the fact that you can write the delta function using what we call its Fourier form. Okay, so in particular, what you know is that 1 is equal to the integral with respect to x of delta x by definition of the delta function. But this delta x, you can rewrite it in another way. You can rewrite it like this. 1 over 2 pi integral with respect to x integral with respect to the imaginary axis. So you're integrating on the imaginary axis a kind of auxiliary variable. It's called the Fourier conjugate, exponential x hat. Yeah, there is a typo in the notes. I will correct it right now. I will correct it after. x, okay? Or if you want, if there is a minus a there, it would be x minus a. Maybe not a, because this is the symbol we use for replica, let's say x bar. So this is the Fourier representation of the delta function. So you see that it's indeed true, because if x is different than x bar, you are integrating this x hat, which one second, I've not done typos. Yes, so this is a complex exponential. This x hat is a complex number. So I'm integrating an oscillating function, and so this integral will be 0 if this is non-zero. So if x different than x bar. Instead, it will be 1, and this is the normalization associated with this integral, only if x equal x bar, which is the same property as the delta function. So it's just a way to represent the delta function using a Fourier representation. Okay? So it's an important trick, because doing so, this delta function will be written in exponential form like this. So we will have a big exponential that we can then continue to manipulate. So let me use this. So I plug this representation here in our previous expression. And so what we get is the following. 1 over 2 pi. So these are coming from the delta functions. I have also an integral with respect to q, and which is a matrix, and q hat, which is a matrix. So the q hat is what I call x hat there. It's the Fourier conjugate associated with the q's. And so I need one q hat AB. I need a q hat AB for every delta function like this. Okay, so I have a matrix of q hats at the end of exponential sum of A different than B, 0k of q hat AB, sum of I equal 1 to n of xia xib minus n qab plus lambda n over 4 qab squared. This is indeed correct. You see, this exponential is like this. It's my delta function. So, and the constraint that was enforcing is that little qab equal to capital QAB, where the definition of capital QAB is just 1 over n sum of xia, xib. So this is indeed enforcing this. I've multiplied both by little n, so I have that this sum should be equal to n times QAB. Perfect. So these are my delta functions. And here you should keep in mind, in the back of your mind, even if I think, that this q hat could be complex numbers. Okay? So we'll comment more on this at the end, but at the end it will not matter complex or real, because even if a priori they are complex numbers, the way we're going to integrate the final formula will be by saddle point. And so we will essentially find a contour in the complex plane for Q and Q hat, and we will realize that the saddle point is dominated by real value. So at the end, in reality, this Q hat will be reals. Okay, and this is a consequence of saddle point estimations. I cannot do a course on saddle point integration, but if you've never seen what it means, I recommend that you take a look. It's a very important mathematical tool. But just keep in mind that even if it is true that here the x hat is integrated over the imaginary axis, I will at the end deform this contour and just select one point in the complex plane, which will be, and this saddle point will end up being on the real axis. So these numbers will not be complex. So that's why I'm kind of dropping right away this notation. But okay. Perfect. So, and you see here now this term, the energy, I've replaced the capital Q, which is the function of the replica's axis, by the little q, because of this delta constraints, the capital Q and little q take the same value. This is what I'm enforcing. So I can replace this by little q. So this is my QAB squared here. Okay? Perfect. So you may wonder, why do we have to go through this delta functions with this Fourier representation? All that, it seems complicated, while for the Ising model it was very simple. For the Ising model, right, I could directly compute the entropy. Yes, this is true, but this is a much simpler problem. So the computing how many sequences of binary variables have a certain mean is a very simple problem. If instead you ask how many, if you ask what is the volume of real vectors weighted by these probability measures such that their angle is little q, and these angles can be different for two different vectors, so you are kind of forcing a set of vectors to have specific angles between them, and you want to know what's the volume of configurations in agreement with these angles. This is a much more complicated problem. You cannot compute it directly. So that's why you need these tricks. Okay? Perfect. So, where are we? We are there, and so look, we have done something very important now. We have linearized in the space of what in physics you would call the real space, which is the space of components of this vector. What do I mean by this? If we look at the expression before some manipulations, which is here. So this is the replicated partition function before the manipulations we've done by identifying this square and so the overlap. Here we have a sum over I different than j, and these terms are coupling, are dependent on both I and j indices. Okay? So you have, this is a coupling in real space. This I and j represent in physics the real space, the real dimensions of the problem. While you have another dimension now, which is this replica space, this replica index. You have multiple copies. But we have this kind of couplings in ij, and what we've done by identifying the order parameter and simplifying is to obtain an expression where you have no more interactions between I different than j. You see, now we have taken care by identifying the order parameter of these couplings, and now we just have a sum over I, right? So the trick is that, of course, the coupling is kind of hidden there, because by these delta functions, you could replace again this by the capital Q squared, and if you expand the capital Q squared, you go back to a sum of I different than J. But here, because of this delta constraint, we could replace this by the single number QAB, and the only place where spins, where variables appear, is this one, and this is linear in I, okay? So by introducing this delta function through the identification of the order parameter, we could linearize this whole exponent in the index I, okay? Which is key. So it's a first level of decoupling, okay? Perfect. And the point is that now we can simplify the integral, because this, concretely, this means what? This means the product over I equal 1 to n of dxia pxxai. So you see that I can also take, I can write all this as this constant, it doesn't matter, integral of product over I equal 1 to n. Now everything is factorized in I. And I will put this integral over q and q hat there. So you see, this n, I can think of it as a sum over I of this quantity. So if you want, I can put this sum over I there. It doesn't change anything. And basically, this sum over I is a product of exponentials over I. This is also a product. This is also a factorized term. So everything is factorized in I. So I can put this product over I outside of the integral. Okay. Minus QAB. And this also, this n, you can interpret it as a lambda over 4 sum over I from 1 to n of this constant. It's just n times the same constant. Plus lambda over 4 QAB squared. And all this integral is to the power n. I have factorized my integral with respect to the vector indices that I call the real space. Okay. This is fully factorized over I now. Sorry, excuse me. Not. It's like this. Excuse me. When you do computations live, of course, you make mistakes. This is the product of this integral over I, but you see that this integral is just n times the same. You see, this is a dummy variable. This xi is just a dummy variable that I'm integrating over. So the integral for I equal 1 or 2 is the same. This is just an integration variable. So I can get rid of this product and just put a power n there. Okay? All right. So there are a few more steps. It's been an hour that I'm talking. We can finish the computation at the next lecture, but we're very close now. We've done 2/3 of the effort. So, okay, I will summarize next time again what we've done, but conceptually what we've done is we started from the system, we have replicated, we just took the same integral k times, we integrate the noise that these integrals have in common, that is really the noise in the problem, the zij's, and we went from independent replicas to coupled replicas, but without noise anymore, which are non-disordered, if you want. And then we identified the order parameter. We've seen that now we are in the same position as the Ising model, where we can recognize that the energy is simply a function of an order parameter, which is not anymore just the magnetization, it's the overlap, which is the angle between these vectors. And by introducing this overlap, we could move forward by introducing its entropy. So we decomposed the integral, this replicated partition function, into an integration over the possible values of this overlap and an integration over the configurations in agreement with that value. This is the entropy. And the energy is just a function of this order parameter QA. Okay, and by doing so, we realized that we somehow succeeded decoupling the problem in the indices I. The exponent became linear in I, which allows us to write down a single integral to the power n. You see that now it's not anymore, this is not anymore a high-dimensional integral. This is a one-dimensional integral. We went from an n-dimensional integral with n going to infinity, which you have no way to compute, into a one-dimensional integral. So of course we have to integrate this also afterwards, but these are also scalars. They do not depend on n. There are few variables. So the high dimensionality has disappeared. This is just a one-dimensional integral to the power n. So now it's something you can compute. Okay? All right.
Okay, sir. So after 1 hour, are we joining or after 2 hours?
In 1 hour, I guess, yeah.
Okay. Okay. So thank you, sir. So we will be joining back after 1 hour at 3:30 as per Indian time.
Okay. See you later.
Okay. Thank you. I thank everyone for patient hearing. Thank you, John Barbier, sir, for your kind, fruitful insights. Thank you.
Yes, good afternoon all. Anyone present in the session? Please switch on your cameras. All are requested to switch on your cameras.
Thanks.
Yes.
So I can assure everyone that it's the last technical lecture. Tomorrow will be very light. I will mostly show you pictures and give additional examples. Okay, so just switch on your brain for last hour, and then it will be easier. Okay, so let me summarize what we've done so far in this replica computation. So, like I said, the goal is to compute the expectation of the logarithm of a random function, okay, where the randomness is this y. And the issue is that it's difficult to compute expectation of logarithms. So the way to get rid of this log is to use the replica trick. So by Taylor expansion, you realize that when you can convert the problem of computing this log moment into computing a normal moment, but at the price of making sense of what's the zeroth moment of this random function. And it's a problem that at the moment we're kind of setting aside, because we're starting the computation for integer moment, for which this is just a normal moment and everything makes sense. We don't need to think too much. And the point is that now that we got rid of this log that was stuck here, this kth moment can be computed, because if you write down z to the k, this is just this replicated integral, and that you can think of the normalization constant of the posterior distribution of independent replicas, right? Because this z to the k is just the normalization of px1 given y times px2 given y, k given y. Each of these p carry a z as normalization, and so the normalization of this whole product measure is just z times z times z to the k. So it's independent replicas, and this is the associated partition function. What will couple these replicas is, again, the fact that we can integrate out now the noise component. So we integrate y conditional on x star. So x star is there. So really, here I've not been precise enough. The expectation that we carried was really an expectation of yij given x star, right? And yij given x star is a Gaussian random variable with this mean and this variance here. So this is just a Gaussian integral, so you can compute it easily using the standard Gaussian integration formula. And we ended up with a formula that looks simpler. So now there is no more noise, and conceptually what we've done is go from a system in z to the k, apart from the fact that we're sharing this quenched randomness, this disorder z, the noise. And by integrating the noise, we gain the fact that there is no more noise anymore. So this is good. But the price you pay is that you obtain a new formula where now replicas are coupled. Okay, so there is no free lunch. So we get rid of something, but we pay the price of coupling these replicas. So now we have terms like this, where A and B interact, okay, in a pairwise fashion, and this term where the A's interact with the ground truth X star. Calling again, just changing notation and calling X star X0, we realize that this integral can be further simplified and made very symmetric. So we have this kind of exponent there with a double sum over A different than B and a double sum over I different than J. So this is the summation in replica space over the replica indices. This is the summation over real space, the components of the vector. And now the goal is somehow to find ways to decouple these sums, is to linearize everything, okay? So the way to do that is to do like in the Ising model, is to recognize that now this exponent can be expressed in terms of statistics of X. It's not a generic function of X, it can be written in a more compact manner in terms of the overlap, the order parameter in physics language. So indeed, one can recognize that this double sum over I different than J can be written as a single sum to the square, okay? Up to a diagonal term that we remove to complete the square, but which is negligible, okay? So this we can then forget it. And when we have done this, we are at the same stage as the Ising model. We can define this kind of sufficient statistics that depends on XA and XB, it's just the angle between them. And so here we have this Q square. So now we have re-expressed the energy of our system, this energy function, for the replicated system, not just the original system. We had to replicate to identify such a simple form. And now this energy is expressed in terms of sufficient statistic of an order parameter, okay? Perfect. So now we need somehow to decompose this integration over the so-called microscopic configurations, so the configuration space of our vectors, our replicas, into subregions corresponding to different value of this order parameter, okay? So it's, you decompose the space of microscopic configurations into macroscopic states. You remember the lectures of yesterday. But doing so, we need, basically we are coarse graining the system. We're going from a microscopic description to a macroscopic description. We zoom out and we are trying to express everything in terms of this overlap instead of the x's. But when you do so, you need to count the number of configurations of the x's that are in agreement with a certain value of this statistic, of this order parameter. So this is where the entropy enters into play. This is the energy, but now we need to count the degeneracy of configurations in agreement with a certain value of the energy, okay? Like we did in the Ising model, where we counted the number of configurations which have a certain magnetization. In the Ising model, we could do that straightforwardly, because it's a very simple model. It was a trivial combinatorics problem. There, it's more complicated. You have like a set of k plus 1 from 0 to k vectors, these replicas. You are trying to understand what's the volume of configurations they cover when you are enforcing this vector to have certain angles between them. You are enforcing all the pairwise angles between them. These are these QABs. And then you are integrating over this kind of frame of vectors, and you are counting the number of configurations such that this frame is fixed, such that they have these fixed angles between them, okay? So it's a complicated geometric problem. You cannot compute it so easily. So the way you do it is you start from the definition of what this degeneracy is, the entropy, which is counting the number of configurations of the x's such that their angles are fixed to some predetermined constant, this QAB. And of course, if you integrate over all these possibilities, you are just integrating over all the space of configurations, right? So you are plugging this identity that 1 is equal to the integral over all possible angles of this entropy into the replicated partition function. In this way, now this object depends on these predetermined angles, these QABs, and the only dependence in the x's is through this capital Q squared. But because of this delta constraint, here I'm allowed to replace this function of the x's simply by these predetermined angles. This is the same because they're equal by this constraint. But now the only place where this x's appear is here. Okay. And now I use this trick that I can rewrite this delta function in exponential form using the Fourier representation of this delta. Okay, so it's a very important and standard trick in physics, but very powerful. So I use this identity that somehow a delta function can be written as an integral with respect to an auxiliary parameter, a Fourier conjugate, x hat, of this difference here, which is this one. Okay. So it's like if you're going to Fourier space, okay? Okay. So if you do so, you obtain this expression. Again, this is our energy, which looks very simple now. And this contribution, this whole exponential, is the entropic contribution, okay? And then we have the integral over all possible angles and the associated Fourier conjugate that enforce by integration these constraints. And we have, of course, the remaining integration over the x's that appear only here now. And the point of all this simplification now is that we ended with an expression which is fully factorized over this index I, because this sum over I in the exponent becomes a product in an exponential. And this reference measure here is also factorized over I by hypothesis, it's a modeling assumption in this problem. So what we obtain is that we have a single integral that appears here, the power n, because this is just a dummy variable. So we went from high dimensional integral, which is not solvable, to something that looks much less scary because it's a one-dimensional integral now. Okay? And the price we paid to go from high dimension to low dimension is that we had to introduce the order parameters, this Q, to identify them, and to introduce the associated Fourier conjugate to write the delta functions in Fourier in exponential form. Okay? But really you gained a lot. You don't have any more coupled high dimensional integral. You have a single one-dimensional integral there. And the thing we need to keep okay. Yes, I was saying that now through these simplifications and the identification of the correct order parameters and the conversion of these delta functions in Fourier form, in exponential form, we managed to fully lower down the dimensionality of the problem. We went from high dimensional integral to a single one-dimensional integral to the power n. So we have decoupled in real space, okay? But of course, another price we have to pay and to keep in our mind is that not only we had to introduce these order parameters, I will also call Q hat from now on an order parameter. But also we have to make sense of this integral at some point.
Sorry to disturb you. Is the screen visible to audience?
Excuse me. No, excuse me. Yes, I thought I clicked.
No, not visible.
Yeah, I'm starting the screen now. Is it now? Yes, okay.
Yes, now it's visible.
Thank you very much. So sorry, I was saying that I will also from now on call Q hat an order parameter. So we had to pay the price of introducing these order parameters, and but what we gained is that we went from a very high dimensional integral of coupled variables, which were these replicas. There was this order which was represented by the noise in the data. Now there is no more noise. It has been integrated out. And there is no more high dimensionality. It's just a one-dimensional integral. We have factorized over the index that was growing to infinity, which is this I index, but it has been factorized entirely. Okay? So this is very good. But another price we have to pay in addition of these new variables that we need to integrate at some point is also the fact that we'll have to make sense at some point of all these formulas when k goes to infinity, right? You need to remember that here all this looks very nice, and because this k has been taken to be an integer, but in reality the replica trick tells us that at some point we need to take k going to infinity to 0. Okay?
Yes, Mr. Om Prakash.
Yeah, I just did, don't worry, it's fine. Okay, perfect. So yes, so let me now show the next steps. Let me open my notes. Okay, perfect. So now that we have factorized this high dimensional index I can rewrite all this as a constant. So the constant here that I'm talking about is just this 1/2 pi normalizations from the delta functions, but they will not matter at the end. Integral of dq hat, which really are matrices of size k plus 1 by k plus 1. And you see, if I have something to the end, this is exponential in n, so I will write explicitly an exponential. Exponential n log of all this integral. And this dxi, now the I index is not there anymore, so I can just integrate over a scalar. So this dx, the x now here will be just a scalar indexed by a. xa, xb minus qab plus lambda over 4 qab squared. Okay, and all this is in the big exponential there. Okay, and I will put, I will even put excuse me, I've done, I could have written something simpler. Yes, I can all the terms that depend only on Q, okay, can be taken out of this integral. Okay, they do not depend on X. So I can factor them out. I obtain the dq hat exponential sum A different than B QAB hat QAB plus lambda over 4 sum of QAB squared, and then the integral, all this with the n to the power n, which is there. And then I have my integral to the power n, which I can write as the exponential of the log of n times the log of this one-dimensional integral. Sorry, it's a k plus one-dimensional integral, but the I index has disappeared. 0 to k dxa pxxa times exponential of sum over A different than B QAB hat xi, there is no more I, xa xb. Perfect. So why have I written all this in this form? Because you see that what we obtain is something of the form dq hat exponential minus n, some action, so in physics we call that an action, that now depends only on the order parameters. So you see this action is defined by this whole exponent, where I factorize the n, and there is no more x. X is integrated here. So this is just a function of q hat. And so this function of q hat plus this function of q and q hat, I call it capital A. It's my action, okay? So the terminology action just comes from field theory, from physics, but it's just a name. It's a function of q and q hat, okay? What is important is that now I precisely have the form that I need to compute this integration, the final integration that remains with respect to q and q hat, by saddle point integration, or if you want, it's a advanced Laplace approximation. Basically, what I'm exploiting is that I have sums of exponentials with a very large exponent, and that the integral is again dominated by the largest. It's a bit more subtle. I should not say largest. It's a bit more complicated because one has to be careful. Remember that these q hats, when we introduce the Fourier representation of the delta function, they are complex numbers, okay, in reality. So really this A, this action there, is a function of complex valued variables, okay? And when you integrate an integrand of this form with respect to complex valued variable, there is no notion of mean or max, because these are complex numbers. So what you have to select, this integral, when n will become large, what you have to select is the saddle point. It means a solution for q and q hat that extremizes this action, such that its gradient is equal to 0, okay? If there are multiple solutions, you should select the one that, in this case, minimize this A, because we have a minus, so that the exponent is maximized. So among all solutions of q and q hat such that gradient of A is equal to 0, we'll have to pick the correct one. But so saddle point integration means this. You have integration with respect to possibly complex numbers of an exponential times an exponent which is very large, and you integrate like this. So it will be dominated by the sum. Okay? So we have the right form to finish the computation. Okay? Perfect. So the action here takes the form. Let me write it. minus sum over A different than B, 0 to K, of lambda QAB squared over 4, which is this term there. Then we have minus QAB hat, which is the coupling term here between the two types of order parameters. And then we have this integral there. And because I factorized a minus there, we have minus this integral. So minus log, we'll write it below, minus log of integral of dpx exponential sum of A different than B of QAB hat XA. X was telling us, so if I was telling us that the limit, now I also take the limit when n goes to infinity of expectation with respect to y of log of z was equal to the limit, and so this I can replace using the replica trick, limit when k goes to 0 plus of, and I'm going to use one of the three forms of the replica trick, which is expectation, log of expectation of z to the k over, and I will take a 1 over n there over nk. Perfect. So the expectation of z to the k is there. So it gives us lim when n goes to infinity, lim when k goes to 0 of 1 over nk integral with respect to q and q hat of exponential minus n, our function of q and q hat. Okay, this is the form we ended up with. So now I need to make an assumption to finish I will need to make two more assumptions that I cannot justify rigorously, okay, which are heuristics. The first heuristic is that I will assume that these two limits, they commute. I can exchange the order of these two limits, okay? So, and this I cannot justify. I can only justify a posteriori because I can prove with other techniques that the final result I'm going to show you is a theorem. But I cannot directly justify this limit at the level of this replica computation. But at the end it's true, okay? So let me put instead k here to 0 and the n here by commutation of the limits. And you see that now I am in position to compute this integral by saddle point. Okay? So this precisely can be computed by saddle point integration. So this gives me limit when k goes to 0 of the, so you see, saddle point means that this integral is dominated by exponential minus the extremum of this, okay? If we were integrating with respect to real variables, q and q hat, you could say that this integral is exponential minus n times the minimum of this function, meaning the maximum of this exponent because of the minus. in the case of real variables. But these are, at least Q hat, they are complex valued variables. So it means that we are thinking in the complex plane. So in the complex plane, you need to take a saddle point. Okay, it's an extremizer. It means a point where the gradient vanishes. There may be multiple ones, in which case you need to select the correct one. But in any case, it will be a point where the gradient vanishes. There is another type of integration of this form, which are called the stationary, wait, I have a blank. Another form of how is it called? Stationary. A stationary phase approximation. Okay, so you see, this integral gives exponential minus the extremizer of this. With this n will simplify with this n, and so what I get is limit when k goes to 0 of minus 1 over k extremum with respect to q and q hat of this action. Okay, so there is no more n. We got rid completely of n now. It's a variational problem that we need to solve over scalar variables. Okay. A priori, here so because I'm doing saddle point integration, I'm working in the complex plane. This saddle point that extremizes this quantity could be anywhere in the complex plane. So really, here when I'm doing an extremization, this Q and Q hat a priori could belong to C, and these are matrices, K plus 1 times K plus 1. So I will write the stationary condition. I will write the gradient of A equal to 0 and solve, and at the end I will realize that the solutions are real. So if you open a paper where people do this kind of computations, they never write this because they know in advance that the solution will be attained on the real axis. Okay, and the reason is that these quantities, they have a physical meaning. They really correspond to angles between posterior samples. They are not complex numbers. So even if you extend while doing the computation to the complex plane in order to use these tricks, saddle point integrations and things like this, at the end, it's a physics problem and solutions are obtained at real values of order parameters. Okay, so that's why physicists would never write this. But here I just do it for you to understand what I mean. Okay, perfect. Okay, so we can still simplify what is going on because you see, now it's a low-dimensional optimization problem in the sense that this k is finite and then we take it to 0. It's not growing with n, so it's low-dimensional. But still, what does it mean? K going to 0 first. What does it mean? Matrices, you see, when k goes to 0, they become scalar. So this suggests that maybe I can reparameterize these matrices in an easier way. And so this is where enters the so-called replica symmetric ansatz. Okay, so the replica symmetric, and that's why these formulas, by the way, are called replica symmetric formulas, precisely because of the ansatz we're going to make there. So the replica symmetric ansatz is the assumption that the extremizer of this action, of this function, takes a special form, which is QAB equal Q for every AB, A different than B, and let's say Q, let me call it Q Q for A different than B, and V for A equal B. So it's a matrix of the form V and Q on the off diagonal, and it's K plus 1 by K plus 1. Okay? So, perfect. And same for Q hat, where you put a hat there, same form. Okay? So it's called replica symmetric because you see it tells you that these columns and these rows they are indexed by replica indices, by posterior samples. And it tells you that if you take replica A and B, whatever are A and B, their angle, the Q, will be the same. Okay? So what does it mean physically, this? Because again, this Q, we know what it means. This Q is this QAB here, which is the overlap between our vectors in high dimension, okay? The fact that we're saying that for any two replica, their angle is the same. So if you sample today your posterior measure one time and another time, and you repeat the experiment tomorrow, you sample you sample it again twice, and you look every day like this, what's the angle between your posterior samples? We are assuming that it's always the same. So it concentrates. It does not depend on the posterior samples. So it's a concentration property, okay? And this you can prove also that it is true using other techniques. It's a whole field of mathematics to show this kind of concentration statements. Myself, I've worked a lot on this. It's very interesting. So here I will not justify it, but you can prove that it's indeed correct. That if you sample posterior measures multiple times and look at angles between vectors of posterior samples like this, it will be always the same. It does not depend on which samples you are considering. Okay. Of course, these samples must be proper samples of this measure. They must not be atypical samples, very rare samples. It could be that if you try this exponentially many times, this experiment, so very, very, very large number of times, at some point you see a deviation. But this event has a very small probability to happen. So it can be forgotten, okay? It has exponentially small probability to occur. Almost all the time, if you sample your posterior twice and look at the angle between the two vectors, it will be a constant, okay? And this constant is what we call Q. Okay, so this is what this assumption is saying. Instead, on the diagonal, it's the norm of a posterior sample. It's the angle between a vector and itself. So it's its norm squared. Okay, which of course has to be different. Perfect. Making this assumption allows to greatly simplify the above formula. Because you see, in particular, where is our potential? Something like this becomes just Q times Q hat times K plus 1. And this, in this integral, in this exponent there, this QAB now has no AB anymore. So I can put the Q hat in front of the sum. And this term also simplifies. It just becomes K plus 1 times the same terms. Okay, so let's write it. With this assumption, the action is equal to K plus 1. We're almost there, I swear. It's almost finished. Minus 1 over minus where is yes, the action divided by K gives this. Okay, perfect. And now we can use again the same trick that we used to decouple at the end the I index, the high dimensional index. Look, we have a final coupling here. This is this term here. It's the coupling between the replicas. Okay, it's a pairwise coupling in the sense of a product between XA and XB for every A different than B. You should be tempted, and you would be right here, to use again a Gaussian integral to decouple this exponent, to linearize this exponent. And this is what we're going to do. So I can rewrite using again the Gaussian formula there. Here. I can use it to convert the exponential of a square into a Gaussian integral. You see, this is linear in B. This is what I mean by linearize. This is quadratic in B, and this is linear in B. But the price to go from quadratic exponent to linear exponent is that you need to introduce an auxiliary Gaussian variable, okay, whose variance is inverse variance A is related to what is the denominator of this B squared. Okay, so this is the linearization trick. You can go from quadratic to linear at the price of introducing a further integration variable. It's similar to what we've done here. We had a function that was quadratic in the variables, and at the price of introducing a new integration variable, actually two, q and q hat, we obtained an expression which was linear in this is I. So you see, you can go always from quadratic functions in exponents to linearized version at the price of introducing additional integration variables. Okay, and this is a very important trick. Because you see, I have to do that in the sense that this expression, if I do not move forward, if I do not further simplify, I cannot make sense of it when k goes to 0. I need to take the limit k goes to 0 from the replica trick. But this is an integral over k plus 1 variables. I can only make sense of this integral when k is an integer. So somehow I need to do something before taking k going to 0, which is the final limit we need to take. So this is what I'm doing now. So this integral can be rewritten by the Gaussian integral, by the Gaussian integration formula, as log of integral product dpxxa. So let me first exhibit the square, q hat over 2 sum of a xa squared. This is my squared minus the diagonal term, which was not present, that I need to remove. And this is my b squared in the Gaussian integral formula. It's my b to the squared divided by 4a. So now I introduce a Gaussian variable to linearize this. This is the same. So really the Gaussian integration formula is used here as log of integral product dpxxa of exponential q hat over 2. Not q hat over 2, sorry. So you do the exercise with the Gaussian integration formula. It's very simple. Square root q hat z xa minus q hat over 2 xa squared, and I have a sum over a there, and I have an integral with respect to z. This is my auxiliary variable. Okay, this is my Gaussian integration variable, which is just a standard Gaussian. Okay, you can just check. You do this integral of this exponent, and you will recover this, which is this. Okay, so it's a trivial exercise. Perfect. And now I claim that we are in a position to take k going to 0. Okay, so it's the final step, and we're done. So now we can finally take k going to 0 in a q hat divided by k. So let's do that. So I claim that the final formula is limit. So the final formula is given by the limit when k goes to 0 of this plus this. And here you see you have a form log of an expectation of an integral to the k, because you see this is fully factorized to the k plus 1, sorry, a equals 0 to k plus 1, and this sum goes from, I can factorize my product, takes everything here. So this is just a single integral log of expectation with respect to z of a single, again, one-dimensional integral. Now it's really one-dimensional, it's not k plus 1 dimensional anymore. A single x to the k plus 1. Okay? So now you see we obtain an expression which is not only factorized over the real index I, which was going to infinity, but now we have also managed to linearize with respect to the replica index using this replica symmetric ansatz. And now I claim that if you have an expression like log 1 over k log of an expectation, let's say with respect to z, of a function of z to the power k plus 1, the limit of this when k goes to 0 now makes sense, and this is equal to expectation of log of this function. So you see, we use again the replica trick the other way around. Here we have k plus 1, before we had k, but you can, sorry, excuse me, make a mistake. Yes, I'm sorry. The replica trick otherwise would be wrong. You can check that this is expectation. Yes. Z, f of z, log of f of z. Because you see, you can write this as f of z to the k times f of z. And at the end, this one will go out, and the log will be reconstructed by this, by the replica trick. So it's again by Taylor, can be verified by Taylor expansion. So you can use this formula, it's like a replica trick again. And if you do so, what you get the final formula. We're done. So the limit I have 5 minutes left, so it's good. So the limit, I summarize, limit when n goes to infinity of 1 over n expectation of log of the partition function of y is given by the limit when k goes to 0, limit when n goes to infinity, 1 over nk log of expectation of z to the k, which ended up being limit when k goes to 0 of 1 over k, our action excuse me. Okay, which gives extremum with respect to q and q hat, where q and v hat, which are these four quantities, v, q, and v hat, q hat. Yes, so in the notes I have not written the v and v hat because excuse me one second. Yeah, excuse me, the v and v hat never appear actually, because you see the only terms that appeared is for a different than b here. So I never need to consider the diagonal of this matrix. So this v and v hat at the end do not appear in the expressions. You can check. There is no v and v hat. Q hat over 2. I will write this below. And here it includes also an expectation with respect to x star drawn from the prior. So here, yeah, there's been a simplification. Okay, using this trick here, which is again this replica trick, you obtain this expression. So this is the final formula. It's the replica formula. So the one I've shown at the beginning of the course, there was no q hat. There was only this parameter q. But actually now if you solve the fixed point equation, the saddle point equation, so let's call all this function f replica symmetric of q and q hat. Now you need to find the extremum. So you need to write the gradient with respect to q and q hat of f q hat equal to 0. You need to solve these equations. And what it will give you, you can just write the gradient equal to 0. It will give you q hat equal to lambda q. So you already see that even if when we introduce delta functions, this q hat were potentially complex variables, the saddle point equations tell you that this q hat is just proportional to q. And q is clearly a real number. It's the overlap. It's an angle. So at the end, everything remains real, okay? And if you plug this into this function, it becomes just a function of Q. And this function of Q is the one that was given at the beginning of the course. It's the replica formula. Okay. Now, if you do instead, so this follows, this equation follows from the partial derivative with respect to Q. And the other equation with respect to Q hat gives the equation that Q verify the self-consistency equation that I gave at the beginning. We have the denoising, the scalar denoising problem with the signal-to-noise ratio lambda Q that appears. Here, if you go back to the beginning of the lectures, you realize that this object that appears in the replica formula is related to the mutual information of the scalar denoising problem, where the signal-to-noise ratio is this Q hat, the Fourier conjugate, which is equal to lambda Q. Okay? So that's it. We obtain the replica formula. Okay, now you solve this stationary conditions, this equation, which is now just a function of Q, because I removed the Q hat thanks to this equation, and you obtain the curves that I've shown at the beginning. Okay, that's the replica symmetric prediction for the MMSE. And then, of course, you should be doubtful about all this. I've made many weird things, many assumptions that I could not justify, and you would be rightful to doubt. But I can tell you that now there are methods to prove that the final result of this method is indeed rigorously correct. And yes. Hello.
Hello.
I'm hearing.
You are audible. Hello.
You are audible, yeah.
Achha.
I could hear you, yes. Okay, you have a question?
Please share your question either on a chat box or directly here.
Say it again. Okay, I don't think it was a scientific question, so it was.
So you can continue. Please continue, sir.
Okay. No, but okay. Yes. So I'm done for this course. So basically, that's it. That's the statistical physics derivation of this replica formula. So it looks involved, but I can really assure you that if you accept these heuristics that I've given you, all the remaining steps are just Gaussian integral or completing squares. It's from the algebra point of view, it's pretty simple. What is not so simple is these commutations of limits between the replica limit and the large size limit. Then to understand what this replica symmetric ansatz means and connect this to the fact that physically it means that the order parameters concentrate onto their mean. So these are the important points, but the computation is pretty simple. So it's in the notes, and I'm pretty sure that most of you can repeat it. Okay, so thanks to that, now we have a complete theory for the spike-Wigner model. We have computed the free entropy, which is basically the mutual information up to an additive constant. You can see in the notes the link between free entropy, which is essentially the Shannon entropy of the problem, and the mutual information. We discussed this at the beginning. So we have this mutual information. By the IMMSE formula, we have the MMSE. So now we have a prediction for the minimum mean square error reconstruction of the spike in this problem. We have analyzed also the reconstruction performance of spectral PCA. So we have an algorithm and the base optimal limits. Okay. The last thing I will discuss a tiny bit tomorrow is this other this Bayesian algorithm, which is approximate message passing, which allows to estimate the base optimal estimator, but without having to really sample the posterior distribution in a smarter way. Okay. But basically now we have already a good strong theory, a good chunk of the equations we need to understand the phase diagram of the Spike-Wigner model. Okay. Perfect. So tomorrow I'll start with discussing for an hour this AMP algorithm. I won't do much derivation. I will just give you the idea behind it, and then I will spend the remaining hour and 2 hours, the last 2 lectures, to discuss many other examples of problems in computer science, in inference, in coding, in machine learning, where these techniques are useful. Okay. Perfect. So if there is a question, please go ahead. Otherwise, we'll meet tomorrow, I guess.
Yes, any questions from the audience side? I think no one is having any question. So thank you, sir. We'll meet tomorrow at 11:30.
Thanks a lot. Goodbye. Have a good day.
Okay. Thank you, sir. Tomorrow 11:30, right? Okay, sir. Okay.
Yes.
Thank you, sir.
Bye.
Thanks a lot. Goodbye.
Bye.